Today we're going to look further into what a function actually is and what a function is actually for. So what is a function? We've kind of looked at functions, we've kind of looked at some numbers and some relationships that are functions. We've kind of, manipulated a little bit of some functions and entering in some values into some functions to solve these equations that we are calling functions. But what truly is a function? So let's look at this. It says, what is a function? Well, let's think about how does the position of the earth relative to the sun depend on time elapsed. Okay, we can represent that with a function. Now, the average person probably can't, but a scientist or researcher in that field can most certainly represent that statement, that English statement right there, with a function. Here's one that we might be a little more familiar with. It says, how many liters of gas will you be able to pump for a given amount of money paid? What type of gas will come out if you press a certain button on the screen? Now, we don't do liters here. We do gallons, but same principle, right? If you go up to the gas pump and you have 20 bucks, you can calculate with a formula, with a function, how much gas you can get for that $20. And it also depends on which button you press at the pump, whether you're getting, say, an 87 grade, an 89 grade, or an 80 or a 91 grade, right? I also have E85 in some situations. I also have 93, 95. I think the highest I've ever seen was 97 at an actual pump there. I've seen jet fuel, but hadn't seen that at a physical gas uh, area where you would actually just get gas for your car. But you should be able to calculate this with what we call a function. This is a functional relationship that we can create an equation for called a function and calculate certain outcomes based upon these variables. One variable being how much money you have, the other variable being what quality of gas you're getting. Let's look at another one. So this one says, what type of drink or snack will come out of a vending machine if you enter a specific code? Even that can be related in a way with a formula. Okay, that formula being a function of the code that you enter, right? And you could even make that more complicated with the amount of money that each particular code has to cost in order to put that drink or snack out of the machine, because it might vary per code, which relates to per item in the vending machine itself. What distance does the train cover over time? What is the speed of a train? Does distance depend on time, or time depends on distance traveled? Okay, so we can certainly calculate what distance a train covers over time based upon how fast it is traveling, or the speed of the train. And that distance is going to rely on both the variables of time and distance traveled. Okay, because obviously I can travel for an hour at 1 mile per hour and not get as far as if I traveled 45 minutes at 2 miles an hour, because I'm traveling faster in the second scenario, even if for a shorter amount of time. Those are variables that can be changed throughout the equation to get a different outcome. Variables that can be changed throughout this function we create on a real life situation to get different outcomes. So let's look at this. It says the cost of the trip. Ian is planning to drive from Toronto, Ontario to Kingston, Ontario. Ian wants to know how many liters of gas needs to go there and back if his car consumes 10 liters per 100 kilometers. He also wants to know how much this gas will cost. Could you help him figure it all out? So we could first go online and research the distance between Toronto and Kingston and record the distance in kilometers in the box. So pause the video and see maps here. And I'm going to go Toronto. in Canada, hit directions, and then Kingston. Okay, so from Toronto to Kingston looks like 8.6 kilometers. Now, calculate how much gas is needed for the distance you have researched. If the car consumes 10 liters of gas per 100 kilometers, record the total amount of gas needed in liters in the box. Okay, if we're going 8.6 kilometers, right, and we're trying to figure out how many liters of gas we need, and the ratio is 10 liters per 100 kilometers, we have a very simple function here where we're multiplying the distance traveled here. So this is your distance times your fuel ratio. Okay, or fuels, you might even want to call it fuel consumption. Yeah. Okay. Now if we do this math, 0.6 times 10 divided by 100. So we're looking at 0. .86 liters of gas that we have burned. Now, this seems like something that you probably could very well figure out on your own and calculate on your own based on the car that you have and the distance you travel. Like I said, here in America, we're going more towards miles per gallon. But hey, you might want to travel abroad. You might need to do some conversions. No problems, right? This scenario in of itself creates a formula. Okay? And based upon that formula that we just did, we can take it a step further. It says next determine how much the gas will cost. If the average price of 1 liter of regular gas is $1.20, how will you determine the total price for the amount of liters of gas you calculated above? Okay, how are we going to determine that? If we know that the cost per liter of gas is $1.20, then all we really have to do is multiply that by how much gas we use. Right? We know how much gas we use. We calculated that in the previous problem. We use 0.86 liters. Okay? You don't even have to put the L in there. Now if I do that simple multiplication there, I'm going to get $1, 1.032. So if I round it to the nearest cent, I'm looking at $1.03 worth of gas. I would probably round it up to 4 just so I don't run out of gas on the way there. But it's not like I'm getting $1.03 worth of gas. When I go to the gas station, I'm probably going to get a little bit more of that just to be safe. At least spending that $5, right? All right, can we identify at least one example of a function in the above situation? If yes, describe it below. I see 2 examples of functions that we have created. We've created a function in determining how much fuel we're going to consume, and we have also created a function in determining how much money we are going to spend. The first function here is so the first function that we created was fuel consumption equals, I'll continue to refer back upwards, distance times fuel ratio. Okay, and then the second function that we created here told us the total cost. Okay, and the total cost was a function of cost per liter, or total price. Yep, the average price per liter of a liter of regular gas. So we'll just say average price times what our fuel consumption was. Forgive me in my spelling. I realized that I spelled that incorrectly here as well. Not too much worried about the spelling here. And it still could very well be spelled wrong, but more so worried about the function in of itself. Alright, let's continue on. Let's see if we can match a function description with its possible equation here. Now, the code for the bag of Lay's original chips is 5436. Okay, now if I scroll down through these equations here, H equals 100S, I'm not really getting any relation there to that code 5436. But if I scroll down a little bit, I do see one with that number in it. I see that this Y equals 5436 being the code for the Lay's original chips. So what do you think Y represents here? Y itself represents Lay's original chips. In order to get Lay's original chips, I need to input the number 5436. That's how I get them. And of course, paying the money too as well, right? Okay, so we've matched the first one up. Very simple formula. How do I get Lay's potato chips? I go to the machine, I enter the code 5436. That is the function that gets me the Lay's potato chips. Let's look at number 2. The train travels 130 kilometers in 1 hour. Okay. The train travels 130 kilometers in 1 hour. I'm going to look for that number 130 because it's got to be some relation to it, right? Now I see the 130 down here. I have a D equals 130T. Okay. So I'm going to zoom out so that we can compare and match the two. So I believe this one is probably going to be the one that matches just based on the number. But let's try to break it down variable by variable. The train travels 130 kilometers in 1 hour. Okay. So our D typically stands for distance. Our distance traveled equals 130 kilometers times the amount of time we have traveled. That's what T stands for. So our distance equals 130 kilometers times the time that we have traveled. Okay, so that's our formula that kind of matches that scenario. You are walking to school. The distance one way is 200 meters, and you walk it in 1 minute. Pretty easy to match this one up right here. Once again, D stands for distance. Okay. 200 is the meters that we're walking. And we're multiplying that by the number of minutes that we have been walking. Because for each minute, we're walking 200 meters. So at 1 minute, we're walking 200 meters. At 2 minutes, we're walking 400 meters. At 3 minutes, we're walking 600 meters. And that is the function that represents that statement. All right. A plane is taking off. Its height above the ground after 3 seconds is 300 meters. Now we have kind of narrowed it down here to where we only really have 2 solutions left. And in either of those solutions, I don't see 3 or 300. But we are in this scenario talking about height, and I do see an h representing height. We're talking about seconds, and I see an s representing seconds. Okay, and if we look at a ratio of 300 over 3 that's given by this problem, that would give us the 100 in that problem. So let's see how h equals 100s can be represented here. Okay, so I'm going to rewrite it down here just so we can see it. Okay, h is clearly height. That equals, okay, if we break it down to the original question, it'd be 300 meters per 3 seconds. Right? And we're also multiplying that times s. S is the number of seconds that we have been above the ground. Okay? So you can even call it seconds flying because we're in a plane. So 300 divided by 3, that's where we got the 100 here in this original equation. That's where the 100 comes from, is the 300 divided by 3. It's just a reduced fraction, right? A fraction reduced to a whole number. And then the seconds is just the number of seconds we've been flying. For every second we're flying, we're gaining 100 meters in height. Very good. Okay. The water tap is dripping at a rate of 10 drops per minute. I think it's pretty easy to match it up here. So the water is dripping at a rate of 10 drops times your time here. We recorded our time, remember, in minutes, which is probably why they used they used T for time, but our time's recorded in minutes. So instead of using M for minutes, we decided to use T. So let me do a quick correction here. It's interchangeable. The letter really doesn't matter, but we definitely want to stay consistent with what is written. So here, minutes is represented by our T for time. Okay. So real life scenarios turning into real mathematical functions. Now let's think about one other little aspect here, domain and range. Okay, there are situations when only certain input values can be permitted, and situations when there are restrictions on the output of the function itself. Okay, so let's think about something really simple, the game of soccer. We can represent the trajectory of a soccer ball as a relationship of the height dependent of the ball and the horizontal distance independent it has flown. Okay, the horizontal distance is the independent variable. The domain is the set of all possible values that the horizontal distance in the situation could be. Will there be a restriction on the horizontal distance, and how do you know? Well, let's practically think about this. We're also going to ask another follow-up question right after that, but let's think about the domain here of the independent variable. All right, I'm going to talk to you for a minute. So, if I'm kicking a soccer ball, I know that there are some very good soccer players out there in the world. Very good ones. But even the best soccer player in the world has their limits on how far the ball can be kicked. Okay? Each player has their own limits on how far they can kick the ball, and we can practice and get better and better and better, but there is a human limit to how far even the best human can kick a ball. So, there are values that a human will never reach when it comes to kicking a soccer ball. Okay? Those values can be affected by a lot of, earthly things in themselves, but also human strength and how far the ball can be kicked. So, there is definitely a restriction on the horizontal distance that ball can travel. Do we know necessarily what that is? No, we don't. But there definitely is a restriction on it. I'm sure you could probably even look up what's the furthest a soccer ball has ever been kicked. And for now, until that's broken, you can assume that that is your restriction. with that, so our horizontal distance here is our independent variable. That's our domain. Our height is our dependent variable. So our horizontal distance is our x. Our height here is our y. Okay, that's our dependent variable. And that dependent variable, that y, represents your range. So just as there is a limit on how far a ball can be kicked by a human, there's also a limit on how high a ball can be kicked by a human. So both of these have restrictions. So just judging by the picture, if this was the highest and furthest ball ever kicked, you can definitely tell that if that is the case, these lines here give you all possible values of how high the ball could go versus how far the ball can go. Okay, so the domain and range live within this semi-little box here. And it's not a perfect box by any means. But if this is as far as the ball could be kicked by the best human there ever was, the ball can never exist outside of this box on the horizontal domain. And if this is as high as the best superhuman could ever kick the ball, then the ball will never exist above this vertical plane here, which is our range. So in many functional situations, there are limits on the domain and limits on the range. Okay. Another thing to consider is we can't kick the ball negative. We can only kick the ball positive distance. And we also can't kick the ball down below a certain distance either. If this is the ground, if this X bar right here is the ground, we can't kick the ball below the ground. Okay. Just as we can't kick the ball backwards. Okay, because even if we kick it backwards, if we turn around and kick it the opposite direction, it has still traveled a positive distance. Okay, so we can't really kick it negative distance. We can only really kick it a positive distance because the direction we kick it still has a positive distance to it. Even if you turn around in circles and kick it the opposite way, that doesn't necessarily make the distance negative. The distance here is always going to be a positive distance. And like I said, we can't kick it below the dirt. So we also have the domain restriction that y has to be greater than or equal to 0, because that's the lowest it could be. And x also has to be greater than or equal to 0. It is possible to not kick the ball at all. That's why I'm leaving a 0 value there. But it's also possible to kick it a really long ways. We don't know what necessarily those upper limits are. We definitely know we can't go lower than 0. So you have to think about the domain and range on some of these functions, especially practical ones. That is definitely something we cover in the Math 108 at USC Aiken that you will need to be prepared to review some different scenarios, right? If we're talking about time, right now we can only travel forward in time. So there is no going back in time. Okay, if I'm gambling money, I can't gamble negative money if that's what the situation calls for. So there are some things to think about with certain things. So if I'm putting quarters into a slot machine, I can't gamble half a quarter. I have to gamble the whole quarter. So just practical situations where certain things can't be done and that domain and that range is potentially limited. So that's what a function is. A lot of functions that we're actually practically going to use are from real life. They're real life situations that are put into functions. We do a lot of representation of mathematical functions to get you familiar with the processes of functions and how to manipulate functions. But the whole reason we do that is so that you can use these functions to represent real life situations and solve real life problems. Okay, whether it's figuring out how much fuel you're supposed to be getting for your money at a gas tank, or how much food you're supposed to be getting for your money at a restaurant, or if you have enough money to pay a certain bill, or how much money you need to pay all your bills. Those can all be generated into a function to calculate something that is going to affect you in real life. So I hope you learned a little bit today. If you have any questions, reach out to me, let me know. Other than that, I look forward to seeing you next time.